I'm super excited to have you here to share more about how you can reach high performance on your ML training workloads using Trainium-based instances and also achieve low cost per training. My name is Nitin Nagarkhatte, and I'm a Principal Product Manager at AWS. And presenting with me today are Ron Diamond, Chief Architect of Trainium, and Hamid Shozan-Azeri, Applied AI Scientist at Meta. Let's get started. AI is everywhere, as we all know. Over the past few years, we've seen a proliferation of new and exciting technologies and experiences that are powered using AI. Whether it's computer vision, language recognition, recommendation systems and personalization, or even robotics and industrial automation, all of the advancements that we've seen in this space are just at the very tip of what we can achieve using AI. Innovators like you are constantly pushing the envelope on getting higher accuracy of prediction and powering new experiences using AI technologies. The main reason that's powering these new capabilities is the size and complexity of modern AI models. As you might all be familiar, in the past few years, the number of parameters per model has been growing at an exaggerated rate, almost 10 times per year, and it just continues to grow at that rate. What we're seeing is that there is this amazing flywheel effect that's driving this exponential growth. As we start building more complicated models and larger models, we see the quality of predictions improve and the array of applications that we can drive using AI also grow dramatically. As these applications grow, we start seeing an increased uptake of these applications that leads to an increase in the demand for compute technologies and acceleration technologies really to power these AI models and serve these to the wider growing audience. And this increasing demand leads to an increase in investment in new research, in fundamental performance analysis, tooling, and optimization techniques. And this investment, in turn, results in not just new fundamental hardware architectures that accelerate AI, but also new AI techniques and algorithms. And all of this algorithmic innovation, as well as hardware architectures, in turn, lead to even more applications and higher quality that we as users can consume. As a result, what we're seeing is this completion of this flywheel effect, essentially a virtuous cycle that keeps on feeding on itself and accelerating growth all around us. As you might have heard, we at Amazon are obsessed with helping our customers. Looking at all of this innovation that can be done using AI, we started thinking about what we could do to actually help you here. So we did what we do best. We started investing heavily in our AI ML services and infrastructure, right from building new accelerator types to servers and software to managed services. Our goal here was primarily to deliver high performance, new capabilities at a much lower cost for all of you. And we are actually working with many of you very closely to take advantage of all of these capabilities that we're bringing and accelerating your own flywheels, creating your own innovation cycles. One of the main areas that we're investing in very heavily is the space of optimized architectures and accelerators for AI specifically to stay ahead of that exponential curve that we just saw a few minutes ago. Inferentia was our first accelerator in this space, specifically optimized to accelerate the inference workload, and training is the same for training workloads. Both of these are built from the ground up to deliver high performance at very low costs. To make it really easy to adopt these accelerators, we also built the Neuron SDK, which is natively integrated into industry standard ML frameworks like PyTorch and TensorFlow. With Neuron SDK, you can easily adopt accelerator instances based on both Inferentia and Trainium without having to make any changes to your underlying AI applications or ML models. As I mentioned before, Inferentia was our first foray in the space. Inferentia is specifically optimized for inference and delivers high inference performance at the lowest cost per inference in the cloud. We launched Inf1 instances back in 2019 based on Inferentia. Each Inf1 server has up to 16 Inferentia accelerators and is capable of delivering 1 petaflop of bfloat 16 compute and 2 petaops of int8 compute. Let's look at performance for a second. In terms of end-to-end performance, Inf1 based instances deliver up to 25% higher performance compared to G5, which is our next best inference optimized instance type, at up to 70% lower cost per inference. This is a huge saving. And we've seen that a lot of users are able to leverage this performance as well as cost saving to optimize their end-to-end performance, user experiences, while still dramatically lowering their operational costs. We launched Inferentia, as I mentioned, back in 2019, and thousands of customers actually leverage Inf1 based instances today, ranging from large customers such as Airbnb and Snap to enterprise customers like Condé Nast, NTT PC, to many fast-moving startups. And many of these customers have been able to achieve amazing results using Inf1. For example, Airbnb was able to achieve 2 times the throughput of GPU-based inference for their PyTorch-based BERT models straight out of the box. In addition, a lot of Amazon's own inference workloads also run on Inferentia today. For example, Prime Video that we're all familiar with, and many Amazon AI services such as Alexa, TextRact, all of these leverage Inf1 instances very heavily. Most recently, we saw Amazon.com move their inference workloads to Inf1 instances, lowering their operational costs by 85% at much better latencies compared to previous instances. This is just amazing progress and traction that we're seeing here. Let's now switch gears and talk a little bit about Trainium, which is the focus of our talk here today. As I mentioned previously, Trainium is our purpose-built accelerator specifically for ML training workloads, and Trainium delivers the highest performance at the lowest cost to train ML models in Amazon EC2 today. Let me repeat that. Trainium delivers the highest performance at the lowest cost to train ML models in Amazon EC2 today. And of course, Trainium is fully integrated through our Neuron SDK with industry standard frameworks, orchestration techniques, and all of AWS managed services. Let's dive a little bit deeper into the TRN1 instances built using the Trainium accelerators. As we all know, the training workload tends to be significantly more compute and network heavy compared to inference workloads. This is why we actually built the TRN1 server to be about 3.5 times more powerful than the Inf1 server that we just saw. Each TRN1 server can deliver up to 3.4 petaflops of bfloat 16 compute, which is about 40% higher than the best GPU-based instance that we have today, which is P4D. Also, TRN1 can deliver 840 teraflops of FP32 compute, which is 5 times higher than the best GPU-based instance we have. This is really important when we think about scientific applications where precision and accuracy of FP32 is much more important than the speed that we can achieve using bfloat 16. To complement all of this, each TRN1 server also has 512 gigabytes of high bandwidth memory, which is powered by 13.1 terabytes per second of peak memory bandwidth. Now, all of this compute horsepower cannot be used effectively unless we have really good network connectivity. This is why TRN1 comes with 800 gigabits per second of elastic fabric adapter network bandwidth. This is the highest network bandwidth that's supported in Amazon EC2 today. And we're not stopping there. Because we see that models continue to grow and the communication needs of these large models just continue to expand, we're now also working on the TRN1N instance type, which is going to double the bandwidth from 800 gigabits per second to 1600 gigabits per second, or 1.6 terabits per second. Sorry. Now, let's talk a little bit more about how we are actually building out these TRN servers. Packing all of this compute capability in a single server is good, but it's just not enough. Modern AI models tend to be very large, as again we discussed earlier, and require thousands of accelerators to actually run efficiently and in a short amount of time. In fact, for ultra-large state-of-the-art models, we see that there are up to tens of thousands of accelerators required to run in a reasonable amount of time. This is why we're deploying TRN1 in the largest ultra clusters that we've built in EC2 today. Each TRN1 ultra cluster has up to 30,000 Trainium accelerators, all of them connected together by non-blocking petabit scale EFN network. Let's pause and think about that scale for a minute. Over 30,000 Trainium accelerators bound together with non-blocking EFA network, all of them combined together delivering over 6 exaflops of highly optimized training compute capability. Now, this scale really helps our customers to scale their large AI models up and down on demand, essentially creating elasticity at the supercomputing level. Let's talk about performance for a second. In terms of end-to-end performance, we've measured Trainium delivering over 1.5 times the throughput of the best GPU-based instances we have today at up to 50% lower cost to train. This high performance and low cost combined together can help you train faster, to iterate more, and even train much larger models within your existing training budget. This is very important, again, given how expensive it becomes to train really large models. Now, let's all put this together in perspective. We built accelerators, the Trainium accelerators, built servers that are really suited to the capabilities here, and expanded them into data center scale, binding them together with the right software services to build the largest EC2 Ultra clusters using Trainium. These are fully integrated into the vast array of AWS services that you're already familiar with, whether it's standard storage services like S3 or FSx, or network capabilities such as EFA. All of these are natively supported on Trainium. Going forward, in terms of orchestration and deploying at scale, standard services like EKS, ECS, or Kubernetes and container services, parallel cluster, batch, are all fully supported on Trainium. For deep learning specific capabilities, like deep learning armies and deep learning containers, are also natively supported on Trainium, which means it's really easy for you to get started with your Trainium-based instances. As I mentioned before, TRN1 is also fully integrated into industry standard ML frameworks like PyTorch and TensorFlow, and is also supported by our managed services such as SageMaker. We launched TRN1 instances about 2 months ago, and we're already starting to see an amazing momentum build up with our customers and industry partners. Customers like Magic and Helixon are already leveraging the high performance network capabilities and innovations in efficient data types that we put into Trainium to train their next gen AI models. We'll talk a little bit more about these innovations in a few moments. Also, we have Hamid from PyTorch with us today to share more about how we are actually building the Trainium PyTorch collaboration and making it really easy to use Trainium-based instances. But before we go there, let's dive a little bit deeper into how we actually designed and built the Trainium accelerators and all of the innovations that we packed into it from our chief architect, Ron Diamond.
Thanks, Nitin. Folks, I'd like to start by taking you a couple of years back in time to the point where we started our Trainium journey. And to set the stage, remember that when building chips and servers, it takes a couple of years, and then they tend to live in the data center for a few years more. And that means that we always need to predict what our customers will want in a few years' time in order to guarantee that our products deliver with high value throughout their lifetimes, just like you've seen in the case of Inferentia. But as Nitin just pointed out, AI is evolving at a very rapid pace, which means that predicting what's going to change over the next few years is quite a complicated task. When dealing with problems like this, I like to always go back to a mental model called inversion. Inversion encourages us to inspect a problem from the opposite direction rather than trying to tackle it heads-on. So in our case, instead of trying to predict what's going to change over the next few years, let's try to predict what's not going to change. And this is indeed a much simpler question to answer. Customers will always want more performance, a better cost structure, and a service that is easy to use. I doubt we'll ever get a phone call from a customer asking us to lower performance or increase prices, or maybe make the service a little harder to use. So we built Trainium around these 3 pillars: high performance, cost efficiency, and ease of use. The Trainium-powered TRN1 instance delivers 1.5x the performance and half the cost to train compared to our next in-line training instance. TRN1 also comes with 800 gigabit per second of network bandwidth to reduce the overheads of scale-out training. And coming soon is TRN1N where we double the network bandwidth and attach 1.6 terabit per second to every instance. The network here is based on our second generation elastic fabric adapter, or EFAv2 for short. EFAv2 delivers low latency and congestion avoidance, which enables us to scale to very large clusters, just like the ultra clusters that Nitin pointed before. So now let's dig into the Trainium features that make it so performant and cost efficient, and we'll start with data types. Machine learning workloads require a massive amount of floating point calculations, and these calculations vary in range and precision, starting from float 32 through the popular float 16 and bfloat 16, and all the way to the emerging configurable float 8 data type. Different neural networks require different data types in order to achieve their optimal accuracy. And moreover, during early research and discovery phases, ML scientists often prefer float 32 for its simplicity and accuracy. But then as they move to train at scale, they'll typically opt for a more compact data type, like bfloat 16 or maybe even float 8, in order to optimize for price performance. And that's especially true for large ML models that are costly to train. That's the reason that Trainium comes with a rich set of data types to allow you to select the most optimal data type for your specific use case. And in terms of compute performance, TRN1 delivers 40% higher bfloat 16 performance and 5x higher float 32 performance compared to our next-in-line ML training instance, P4D. Now let's go one step deeper into training with compact data types. One of the challenges that ML scientists face is that training with compact data types doesn't always lead to the same accuracy as training with float 32. And one of the techniques that people use in order to deal with that is called mixed precision. With mixed precision, we move some of the tensors to bfloat 16 or some other compact data type, but keep other tensors at float 32. And this works, but it adds cost and complexity. Trainium fully supports mixed precision, but let's see how we can do even better than that. One of the main contributors to the accuracy loss during training is the rounding operations. Most computer platforms today implement a form of rounding that is called round nearest even. And round nearest even is very similar to what all of us learned in school. Numbers are always rounded to their nearest representable value. So for example, if we round towards integers, 0.9 will always get rounded to 1. And 0.2 will always get rounded to 0. And at first glance, this seems OK. But here's where it can hurt accuracy. Think about adding two numbers together, a weight value of 1 and a small gradient value of 0.2. After addition, we get 1.2, and after rounding, we're going to get 1. But even if we add 10 gradients of value 0.2 to a weight value of 1 and round after each step, the result is still going to be 1. And you can intuitively see that we lost some precision here. We would expect that if we add 10 times 0.2 to a weight value of 1, we'll get a result that is closer to 3, not to 1. With stochastic rounding, this problem is resolved. On every rounding step, we round either up or down in a probabilistic manner according to the relative distance from the two nearest representable values. So in our previous example, 1.2 will have 80% chance of being rounded to 1 and 20% chance of being rounded to 2. And over large computations, just like we have in ML, this tends to average out and provide with more accurate results. Trainium natively supports in hardware both round nearest even and stochastic rounding, and it's your choice which rounding mode to use. We've seen that by selecting stochastic rounding, we can speed up certain models by up to 20%. And this is super simple to use, by the way. You just set an environment variable, and that's it. Trainium takes care of the rest. Now let's look on a real-life example of the benefits of stochastic rounding. And in this case, we'll use a GPT model with 6.7 billion parameters. Here we have a loss convergence graph on the left and a throughput graph on the right. And our goal is to minimize the loss value during training while achieving the maximum possible throughput. We start with flow 32, where the loss convergence is great, but naturally, throughput is suboptimal. Now we'll move to bfloat 16 with round nearest even. As you might have expected, throughput improves a lot. But loss convergence is not as good as it was with float 32. And that's exactly what we discussed before. As a last step, let's do bfloat 16 with stochastic rounding. The throughput is identical to bfloat 16 with round nearest even. And again, that's because Trainium natively supports in hardware a stochastic rounding. But the interesting part is that the loss convergence looks almost indistinguishable from float 32. So we truly get the best of both worlds with bfloat 16 and stochastic rounding. All right, enough data types. Let's switch gears and talk about dynamic execution. As we established, we deeply care about providing you with the highest possible performance. But at the same time, we don't want to compromise on flexibility, which ties into ease of use. And architects often need to trade off between the two. Think about the CPU, for example. It's programmable and highly flexible, but it's not optimized for a specific workload, like machine learning. And on the other hand, hardware accelerators are extremely optimized for a specific workload, but they're not as flexible as CPUs. To get the best of both worlds with Trainium, we coupled a control CPU with a highly optimized purpose-built data path. The control CPU handles instructions like conditionals and loops, while the purpose-built data path handles the number crunching at wire speed. This architecture enables dynamic execution and thus improves the programming experience without compromising on performance. But we didn't stop there. We also deeply embedded vector processors inside the Trainium compute units. And when I say deeply embedded, I mean that the vector processors have direct access into our purpose-built engines and their caches, which allows for ultra-low latency and very high bandwidth. This architecture allows you to run custom operators directly on the Trainium compute units without needing to move data back and forth between a CPU and a coprocessor, enabling high flexibility and high performance together. All right, so far we talked about a single Trainium device, but as we discussed at the beginning of this talk, models are becoming larger very quickly, which makes distributed training a necessity. And when we do distributed training, we typically use collective communication operations, or collective ops for short. Collective ops move data between the different workers and also perform a collective computation on the data as it is being moved. The performance of collective ops is critical for distributed training, especially when training on very large clusters. So let's say our TRN1 improves the efficiency of such collective ops. One of the most popular topologies that is used for collective ops is a ring topology. But ring topologies have a known downside. They don't scale well. As we add more workers to the ring, the number of hops to traverse the entire ring grows linearly, making latency a problem at scale. But if we take a closer look at the Trainium interconnect, we can identify an opportunity to improve this. We have a local chip-to-chip interconnect that is very low latency, very high bandwidth inside each one of the TRN1 servers that connects the training devices with one another. And we also have a server-to-server EFA v2 interconnect. And the key observation here is that the two interconnects are independent of one another, which means that we can send traffic on both interconnects with zero interference between them. And this allows us to move to a 2D ring topology. Here we leverage the associativity of collective ops that perform a computation like summation and perform a sum in each one of the TRN1 servers first, and then perform sum of sums between the servers. This way, we move exactly the same amount of data between the training devices, but we do it via much smaller rings, which means that this topology will scale much better. Let me show you how it looks like when we benchmark a collective communication op on this topology. So here we benchmarked all reduce which is one of the collective ops. We did it on the two topologies, the flat ring all reduced in red, and the two-dimensional ring in green. We're measuring compute time here, so the lower the better. And as you can see, while the two topologies achieve similar performance for a small number of training devices, the 2D ring topology scales significantly better to a large number of training devices. And you don't need to do anything to realize these gains. It all happens out of the box. With all the capabilities that we discussed, let's see how TRN1 performs. Here we benchmarked a neural network called BERT Large. We trained it on a single instance and also on a cluster of 16 instances. TRN1 is shown in green and compared against our next-in-line ML training instance, P4D, in red. As you can see, a TRN1 cluster achieves 1.6x the throughput and 2.4x lower cost to train. All right, nice. So we talked a lot about the hardware. Now let's talk about the software that powers the training devices, the Neuron SDK. Neuron integrates Inferentia and Trainium into popular machine learning frameworks like PyTorch and TensorFlow. This enables you to compile and run your favorite machine learning models on the Inferentia and Trainium targets with minimal lines of code, just a few lines of code. Our goal here is to provide you with high performance out of the box, with no need for model changes or performance tuning efforts. One of the main neuron components that allows us to achieve this is the neuron compiler. The neuron compiler performs just-in-time compilation, which means that it processes the computation graphs as they become available by the framework without an explicit compilation step. The first phase of the compiler is called the graph optimizer. Here we perform most of our hardware-agnostic optimization, like operator fusion and common sub-expression elimination. At the end of this phase, we take each operator in the compute graph and represent it in a loop format. And then we enter the second phase, the loop optimizer. The loop optimizer determines the optimal layout for each tensor and then enters a series of loop transformations, like tiling, vectorization, pipelining, and quite a few others. And at the end of this phase, we take the inner loops and map them into hardware intrinsics, which are fully executable by the training devices. Then finally, we enter scheduling and allocation, which efficiently manage hardware resources. The allocator minimizes data movement by keeping data local in the caches. And the scheduler reorders instructions in order to make sure that we overlap communication and computation and also achieve high levels of instruction-level parallelism. But Neuron is much more than a compiler. Neuron is a full SDK that integrates seamlessly with internal and external ML libraries and packages. And we constantly work to evolve it. Just over the past year, we added support for distributed training libraries, eager debug mode, collective communication optimizations that we discussed before, and a few other features. One of the nice benefits of Neuron is that your performance will keep improving over time as we keep optimizing the different parts of Neuron. One of the notes that we love getting from customers is when they tell us that they just updated to the latest Neuron version and saw a noticeable performance improvement. As part of our ease of use effort, the Neuron team is also collaborating with the community. And one of the teams that we love collaborating with is the PyTorch team. I'm excited to have Hamid with us today from the PyTorch team to tell us about the great work that the two teams are doing together.
Thanks, Ron. Given the state of the AI in this space and large-scale training become a norm across the industry, we all are looking for performance and skill. At PyTorch, we love the variety in the ecosystem that helps our users to develop and scale their solutions easier and more efficiently. And Trainium is a great addition to the hardware ecosystem. As Ron mentioned, we worked very closely with Trainium team to optimize for both high performance and ease of use. Let's see how we are delivering these promises over the software stack. Ease of use and debuggability are the core principles of PyTorch, and we achieve it through eager mode execution, where you build your compute graph dynamically. However, eager mode does not allow for global optimizations of the compute graph, and it limits the performance. So to deliver both performance and ease of use, we came up with PyTorch XLA, where the idea is you take an eager mode program from PyTorch, you make a graph out of it, then optimize that graph to run efficiently on Trainium devices using XLA and Neuron compiler. PyTorch XLA under the hood is using lazy tensors, where we record the sequence of operations into an IR graph, and we only call the compiler when we encounter a barrier. And then the resulted HLO graph will be sent into Neuron compiler for further optimizations and run efficiently on Trainium. This gives the eager mode user experience along with the full performance of Trainium devices. We also added JIT cache to hide the compilation overhead. This means if we encounter any graph that was compiled before, we are going to use the cache version. Basically, if you don't change your input, output, or intermediate shapes, we are going to use the cache version of the graph, so your compilation overhead will be 0. This is a summary about the compiler stack, but let's see how it looks in the code. It requires really minimal changes to your code, just few lines of the code. And first, you need to import the Torch XLA, then the core model from XLA, and really 2 lines of the code in your training loop. So here, you want to basically insert a mark step as a barrier that tells the XLA how where to start compilation. And then you want to pass your optimizer into XLA optimizer step that take care of stepping your optimizer. That's all what you need to run your model on Trainium. So let's see how we are getting performance and scale using Trainium. Trainium natively support mixed precision for B-float and FP16, which is very important to make your training performant. To use mixed precision with Trainium, you can actually use the familiar PyTorch AutoCast context manager. And we have seen some very good results with training with B-float 16 up to 5x speed up, and I highly recommend you guys to work with B-float 16 if you are using Trainium. Then to parallelize and scale your training job over multi-device and multi-node, you might be familiar with distributed data parallel from PyTorch, where it allows you to run your training job using multi-workers on multi-devices. To use distributed data parallel or DDP with Trainium, this is fairly easy. Again, just 3 lines of code. So you have to initialize your process group with the XLA backend. Then you need to wrap your data loader with XLA multiprocessing device loader. And finally, again, you pass your optimizer to XLA optimizer step, where it does the all reduce and actually step your optimizer. On the same note, what if your model is big enough that it doesn't fit into one Trainium device? What if you need model parallel? Trainium natively supports all the Torch distributed primitives, and is adding support for FSDP, or fully sharded data parallel, which allows you to train a much larger model using the same amount of resources. This is a new addition in PyTorch, and it's going to be available on Trainium very soon. Also, we all know about the importance of monitoring and debugging when we are training our models. And Trainium comes with an extensive toolset for monitoring and debugging. We have Neuron LS, which is great for device discovery and topology information. Then we have Neuron Top, which is a real-time visualization of the neuron cores, vCPUs, and all the host and device memory and the breakdown of their allocations. And these informations are also available in JSON format if you use Neuron Monitor. Trainium also supports TensorBoard that help us to monitor our training progress, things like loss, convergence, grad norms, and etc. At the same time, it actually provides a very detailed drill down of the operators, and that helps you to narrow down the performance issues and optimize them. These capabilities are critical, and they tie back into core principles of PyTorch, ease of use, and debuggability. So we are very delighted to work with the Trainium team to come up with an end-to-end solution which is performant and easy to use. So to reflect on the scale and performance, we have seen some great results with Trainium on multi-node. We have seen this linear scaling from 1 to 16 nodes for models such as BERT and GPU with a scaling factor of 93 to 94%. A scaling factor here means that this is a normalized throughput over the number of nodes compared to one node as the baseline. It means if you threw X more nodes on your training job, you are going to get X time higher throughput, nearly X time, 93 to 94%. This is an ideal situation, and I guess every ML engineer would love that. So we are looking forward to hear your experiences with Trainium, and we are happy to help you to get started. With that, let me pass it back to Ron to walk us through how he's going to put everything together. Thanks, Ron.
All right, folks, we covered a lot. Now let's step back a little bit and see how the different features that we covered today come together in order to train a large language model on Trainium. As an example, we'll use a GPT-3 model with 175 billion parameters. One of the challenges when training such large models is their huge memory footprint. For every single parameter, we need 16 bits for the weight, 16-bit for a gradient, 32-bit for a master copy of the weights, assuming we go with mixed precision, and 64-bit for the optimizer state. So in total, we get 128 bits, or 16 bytes, of memory footprint for every single parameter. And if we do the math, 175 billion parameters times 16 bytes per parameter, that's 2.8 terabyte of parameter memory footprint. And so far, we only counted the parameters. In practice, we also need to allocate memory for intermediate state, like activations. With this, it ends up that we need at least 16 or about 16 instances in order to fit such a large model in memory. And in practice, we'll train on more instances than that in order to train in reasonable time. Now let's see how this changes when we move from mixed precision to bfloat 16 with stochastic rounding. The weights and gradients are still 16 bits. But the master copy of the weight can be completely eliminated because we already have a 16-bit copy of the weight. And the optimizer state can be now cut by half, from 64-bit to 32-bit. So all in all, we reduced the per parameter memory footprint from 16-byte to 8-byte. Here it is. And the total memory footprint is cut by half accordingly, so from 2.8 terabyte to 1.4 terabyte. And with these changes, again, bfloat 16 and stochastic rounding, we can now fit this model on 8 instances instead of 16. And this is not just a counting exercise. By fitting on a smaller number of instances, we can reduce the communication overheads during scale-out training. As a reminder, TRN1 and TRN1N come with much more bandwidth compared to our next in-line ML training instance, P4D, which means that their communication overhead is already lower. But with bfloat 16 and stochastic rounding, we can drive communication overhead even lower than before, and thus improve hardware efficiency and lower all end-to-end training time. Nice. So we cut down on communication overheads. Now let's go one step further and try to cut down the amount of compute that we need to do during training. As a reminder, GPT-3 is built out of a stack of transformer decoder layers, and each decoder layer is built out of two main components, a masked self-attention operator and a two-layer feed-forward neural network. GPT-like models are often used in order to predict the next word in a sentence. This can be used in various different applications, including question answering, code companion, and quite a few others. So with that in mind, let's take a deeper look into the masked self-attention operator. This operator is responsible for assigning an attention level to each one of the previous words in the sentence as it tries to predict what the next word should be. And note that we only pay attention to the previous words in the sentence, meaning that attention to future words in the sentence is going to be zeroed out. And this leads to a sparse result, or more specifically, a lower triangular result matrix. Knowing that, and having the deeply embedded vector processors that we discussed before, we can now build a custom sparse attention operator that skips all the computation that is going to be zeroed out anyhow. So by doing that, we can do less computation during training and thus drive the end-to-end training time even lower than before. So with this set of optimizations, and quite a few others that we didn't have time to cover today, TRN1 delivers 1.5x the throughput and half the cost to train. You can use that to cut your training budget by half, or alternatively, to do double the amount of training under the same budget. Just before we wrap up, I wanted to also give you a glimpse into what's coming next. We're investing heavily in both the Inferentia and Trainium lines and are fully committed to deliver you with best-in-class deep learning infrastructure. This week, we announced that the Inferentia 2-based Inf2 instance is now available in preview. Inf2 delivers 2.5x the compute performance of Inf1 and 15x more memory bandwidth. Inf2 also comes with a dedicated chip-to-chip interconnect between the Inferentia 2 devices that is especially optimized for deploying large language models, just like the one that we discussed today. So folks, as we shared with you today, we're investing heavily across the stack, from hardware to software to algorithmic innovation, in order to deliver you with best-in-class deep learning infrastructure. TRN1 is the most cost-efficient, high-performance deep learning training instance that we've built to date, and it's available. You can launch one today and take it for a spin. The QR code on the corner there will take you directly to our landing page and can be your first step into 50% more performance and half your training costs. Folks, thanks very much for being with us today. We really appreciate your time. Please don't forget to fill the survey. And I think we have a little bit of time for questions, not a lot, and we'll stick around in the hallway after if you'd like to chat. We will be happy to.